Okay, so here we go. We've nearly done. Quick summary, this is where we're up to. We've got this equation for D. We've got that because we've set the KE equal to the EPE, the elastic potential energy. The formula is Q1, Q2 over 4 pi epsilon naught times by the distance between the centres of the two charges. This formula gives you how much energy gets stored in the electric field between two charges, Q1 and Q2, if they're separated by a distance d. In the Bible, I think it calls it r, but you've got to get used to that. R is often used for distance, d could be used for distance, even x is used for distance. So we've just set the kinetic energy equal to this. We converted it into joules first, remember, then we put all the values in, and now at the exciting bit, a little bit of rearranging, we can find d, which is the distance of closest approach. So we just swap that round, d comes over to here, and the 8 times 10 to the minus 13 goes underneath. So we got all of that, they swap places basically, the d comes over to the other side. Put all the numbers in. I'm going to let you do that. It's good practice. And I'm hoping you get 4.546. A bit clumsy there with my decimal place. Let's tidy that up a little bit. In fact, I'm going to tidy the whole lot up because this is the final answer. We want it to be legible. 4.546, and the calculator goes on and on and on, times 10 to the minus 14 meters. So that's what your calculator should show you. There's D. We're not going to lose a careless mark. We're going to give it to 2 sig figs because originally the energy of the alpha was given to 2 sig figs. I gave it to 5.0 MeV. So there we are, our final answer with units, which is 4.5 times 10 to the minus 14 meters. So the alpha particle has got incredibly close to the nucleus. And remember, the whole point of doing this distance of closest approach is because if we look back at this diagram, look, it gives us the upper limit, if you like, for the sort of the size, the radius of a gold nucleus. A rough and ready approximation, if the alpha particle here, look, has got within, you know, this tiny number, 4.5 times 10 to the minus 14 of a meter, then that means that's an upper limit for the radius. The radius can't be bigger than that. So the actual radius here, look, there, the radius of the gold nucleus has got to be less than d. So the gold nucleus is pretty tiny, less than 10 to the minus 14 of a meter. And as it says in the key point sheet, we think of the radius of nuclei. So nuclei are typically of the order of times 10 to the minus 15 meters, which fits really nicely with this. As I just said, it's got to be smaller than that. Thank you.